This meeting is being recorded.
Let's take a look at the next sample exercise from chapter 14, sample exercise 4. And in this example, we are asked to find a few different things here. So first, we're asked to find the rate law for this reaction in part A. Then in part B, we're asked to determine the rate constant, which is K. And then in part C, we're asked to determine the rate of the reaction if we changed concentrations of reactants A and B. So let's take a look at what we have to start here. So first we're given 3 different experiments here, experiment 1, experiment 2, experiment 3, and each of which we're given different concentrations of reactants A and B and the initial rate in molar per second as the unit. So the reaction that we're told occurs is this generic reaction up here, where A plus B yields C. And again, we have the initial rates of these reactions. And if we were to compare the rate of reaction 2 to that of 3, we could see that there's quite an increase here, but we wouldn't be able to determine which of our reactants was responsible because we change both A and B between reactions 2 and 3. So we have to be strategic in which of these rates we compare and which experiments we use to determine the order with respect to each reaction. So when we write a rate law, remember we would have this form here where whatever the exponent is tells us the order with respect to that reactant, in this case A and B. So if we wanted to find the order with respect to reactant B, we could choose reactions 2 and 1. Because in that reaction, we hold A to be constant. That remains 0.1. So let's take a look here, and let's solve using reaction, rather, 2 and 1. So if we were to put, there's some delay there, reaction 2 on top of reaction 1, we would see that we have the same K's in each reaction, so they would cancel out. Then we have the concentration 0.1 for reactant A. That will also cancel out. And then the important bit of information here is 0.2 to 0.1 concentration for reactant B. And now we're going to make sure to put the rates in the right area. So we have 4.0 times 10 to the negative fifth for both rates. So what this shows us is if we were to divide the concentration here of B, we would get 2.2 divided by 0.1 raised to the n, and that equals 1 because both of these values are the same. So 4.0 to the negative 5 divided by itself will give you 1. The only exponent that would give you a true statement here would be if n equals 0. So what this tells us is that reactant B has a 0th order relationship to the rate of this reaction. So if we double the concentration, the rate doesn't change. So in our rate law, we will not include B. So let's take a look at what we will include here. So say we compared now reaction 3 to reaction 1, we could solve for the order of the reaction with respect to reactant A. So I'm going to take reaction 3, put that over top of reaction 1. And again, this is because we are changing the concentration of A. So I'm going to put the higher concentration on top. And remember, I do that to make the math a little bit easier. Instead of having a half, if we divide 0.1 by 0.2, if we keep the larger value on top, it's usually easier to do the math. And then we see here, we have the same values for B, so this will just cancel out. as does our K. So if we equate this to the rates now, we'll see that we have 16 times 10 to the negative fifth over 4 times 10 to the negative fifth. And since we have the same exponents, we can just do 16 divided by 4. And over here, we have 0.2 to the m divided by 0.1 to the m. So our equation now is 2 to the m equals 4. And the only scenario where we could get a true statement here would be if the exponent is equal to 2. So my final rate law would look something like this, where A is going to be represented, and we would put that to the second power, but B is nowhere in the equation because it is a zero order with respect to B. So let's see if we can use our rate law and solve for the rate constant now that we have this rate law. So again, we're going to rewrite that our rate equals K A squared. So if we want to solve for our K value here, all we have to do is plug in some value of A and a rate that corresponds to that. So let's take a look at reaction 1. We have the concentration of A is 0.1 and the rate is 4 times 10 to the negative fifth. So I'm going to, again, set this equal here, 4.0 to the negative fifth molar per second is going to equal my K. And then we have over here 0.1 molar squared, right? I'm plugging in my A value here, and I have to square it in this rate law. So I'll rearrange this equation, and we would have 4 to the negative fifth over 0.1 squared. And so this would end up giving us 4.0 times 10 to the third, and let's keep track of our units. So this would be molar squared. This was molar per second. So one of these molars will cancel out with this one. So we're going to end up with our units here of molar -1 seconds to the -1. So be careful when you calculate your units for your K, for your rate constants. And the last part of this equation, or this problem here, asks us to calculate the rate when we have this specific concentration for A and this specific concentration for B. So again, we know that our rate is affected by the concentration of A and not by B. So we're going to plug in our K, which what we just found to be 4 to the third power, molar -1 second -1 for our units, and then we're going to multiply that by the value of A here, so 0.05 molar, and square that. So this will cancel out with one of our molars. Our units will end up being molar per second, and we end up with 4 to the third power times 0.5 squared. So we end up with 1.0 times 10 to the negative fifth molar per second. So we'll continue in the next video, and we'll take a look at sample exercise 4.5.